All right, so to keep going with what we were talking about, kind of a switch of pace, now we want to talk about graphing. Now, you are, or should be, familiar with the exponential growth function graph for this one, all right? Y equals 4 to the x. This would be fantastic if your money was doing this, okay? Because it means it's growing by a factor of 4 times every year. Okay, completely unrealistic, but man, that would be awesome. Well, what we want to talk about is the inverse. Now, we have described it already. We looked at rewriting something. In fact, if we went through the same process and we said, okay, so we've got y equals 4 to the x, and we wanted to change it to its other form, right? If I was just straight changing it to its other form, so these forms that I'm going to write are exactly the same, they just look different. And we talked about having a base, and then we talked about having an argument, and then we talked about having it equal an exponent. Okay, so if I rewrite it exactly the way you and I have done all the other questions so far, the base is 4. You can see that, right? We know to put the exponent on the other side, and then the argument is the only thing left. Now, if we switch x and y, because that's how you find an inverse, what we end up with is something that looks like this. Y equals log base 4 of x. Okay? So this blue one right here and this green one right here are inverses of each other. Now, we have described in past lessons what happens when you switch x and y. And we have described that and said, okay, if you're switching x and y, then that means what you're going to get is a reflection across this line, y equals x. So, what is that going to look like? Wherever you had a y-intercept here, you now have an x-intercept over there. And what you would end up with is a shape that looked like this. So the purple part is the logarithm graph. The green part is the exponential function. Now, which one of these has that same shape? Yeah, that would be the last one here. So, the green one is y equals 4 to the x, and its inverse. Now, one way you could write the inverse would be x equals 4 to the y power. And I know some people would be like, I like that way better. But if you want it solved for y, we have to rewrite it into its other form, which would be log base 4 of x. Now, every logarithm graph looks very similar with few changes. All of them look like this purple one. Why does it look like it's not moving? The timer's just stopped. Oh, okay. It's having a difficult time. Sorry, I was looking at my timer and it looked all weird. Oh, pause that. Paused? I don't know if it's paused. I feel like I'm going to continue. Okay, so the point I'm trying to make here is every time I ask you for a log graph, you're going to get a basic shape that looks like this. Okay, the exponential growth functions look different, but the logarithm graphs all look like this basic shape. And we are going to talk about domain. The domain of this, x is greater than 0. Now, why can't it be equal to? Because guess what this line is right here? You guessed it, it's an asymptote to the graph. So just like the exponential growth functions had asymptotes, so do the log functions have asymptotes. Well, it has one asymptote. Now, what about the range? Well, this thing is going to keep going up, up, up forever and ever and ever, down, down, down for forever and ever and ever, so that would be your all reals, or you can use that phrase, all reals, whichever you prefer. Whoops, off screen. Squeeze it in there. So whichever you think would be better. All right, 18. Graph that thing. Hopefully you realize that's exponential growth. That's exponential decay. This is an upside down logarithm graph. This is the only one that looks like the right side up version of it. I wonder how many questions I have here. Oh, there. We're good. This video might not be as long as I thought it was going to be. Okay. So, what happens? Now, what I want you to notice is that this is not the same as this. Oops, sorry. My base got all messed up. Log base 5 of x plus 1. It's not the same thing. So don't treat it like this is. This one would be left 1 unit because the change is happening inside with the x, and we've always said if it's inside with the x, it's opposite of your common sense. But this one is on the outside, so it's affecting the up and down movement. And we said that matches your common sense. So I'm hoping that you say, oh, that's up 1 unit. So I'm looking for a logarithm function. You know, we know all the logarithm functions have kind of the shape to them. And it's been shifted up 1 unit. Well, if it's been shifted, oops, sorry for yawning. If it's been shifted up 1 unit, there is no change in that asymptote. So that asymptote is right there. We can't cross that line. So that gets rid of that choice. A looks like an upside down logarithm graph. D is the only one that looks like the logarithm graph, and it looks like it's been moved up 1 unit. So we are going to start looking for left, right, up, down. So be prepared for that. All right, now find the domain of the following logarithm function. Okay, so which way has this one been moved? Hopefully you say, oh, that's inside, so that's got to be either left or right, and because it's opposite of our common sense, you said left 5. So imagine I took this regular old logarithm function and I went 1, 2, 3, 4, 5. And so my vertical asymptote is now over here at -5. What we're going to end up getting is a shape that looks like this. If we go through the process of understanding or thinking about pushing all the values onto the x-axis forever and ever and ever, what you're going to find is that we have x values greater than, but not equal to, -5. We cannot cross that boundary line. Now, question 21. I don't really like question 21 all that much. Okay, because it's kind of a little bit, this would be like an extra credit question, to be quite honest. Because what we really have here is log -x minus 7. Now, I know you're probably saying, well, what does that matter? because it's had a reflection done across the y-axis. So now it's true that 3, 4, 5, 6, 7, right? It's true that it has a vertical asymptote because it got moved 5 or 7 units to the right. But because it reflected across the x-axis, it's doing one of these things. I'm sorry, reflected across the y-axis. So it got reflected. That negative right there caused the reflection across the y-axis. So my domain would be x is less than negative or positive 7. But not equal to. Question 22. Find the inverse of this function. Okay, so remember the process is switch x and y. Oh, it'd be nice if I listened to my own instructions. Now we need to go through the process of solving for y. Okay, so we haven't done a lot with this, but all we're doing is changing it to its other form. We have a single logarithm, so we want to change it to base to an exponent equals some other value. So, what's the base? Now, I did mention in the last video that when you don't see the base, you automatically know it's 10. That's called a common log. Cannot spell common to save my life. Common base. Common log. I should say common log. And then base equals 10. Okay? Well, then there's the exponent. Well, that has to be x, because we know that a single word synonym for logarithm is exponent. The only thing left is y plus 2. Now, if you want y by itself, of course the 2 has to move. So, 10 to the x minus 2. That is the inverse. That's all there is to it. Switch x and y, and then go through the process of finding or solving for y. Now, we'll have to see if that's enough practice. We might have to do more practice on that stuff when I get back from my small little vacation here. Down to see my son graduating from basic training. Okay. You should probably start the next video, since this one is a shorter one.